Welcome back. In this section, I'm going to go even deeper into the dimensional modeling side of data warehousing that we started exploring earlier in this series. You will see that the fact tables are not just one thing. There are actually four different types of fact tables, and each one is designed for a very specific use case. We'll break them down into four types, that is transaction grained fact tables, periodic snapshot fact tables, accumulating snapshot fact tables, and the interestingly named that is factless fact tables. We'll also compare the structural differences between the dimension table in a star schema versus a snowflake schema, so you can see how the design changes depend on the modeling approach. Expect a lot of examples and walkthrough throughout this video. So let us continue our journey into the dimensional modeling and go deeper into the world of data warehousing. In the previous section, we got introduced to the idea of star schemas and snowflake schemas, and we briefly saw what each one looks like at a high level. Now, let us get a bit deeper and really understand how these designs work in practice, along with plenty of examples of how dimensional tables are structured inside a data warehouse. But before we jump into schemas themselves, let us quickly revisit a few core concepts because they're important for understanding the bigger picture. Now, when we use the word dimension in data warehousing, we are talking about something that gives context to our measurement, which we usually call facts. For example, if sales amount is a fact, then customer, product time, or location could all be dimensions that help explain that measurement. Now, one thing that often confuses people is that a dimension and a dimension table, they are not technically the same thing, even though people casually use those terms interchangeably. In this discussion, we'll clearly see the difference between the conceptual idea of a dimension and the actual database table that stores its data. Whenever I say table, I specifically mean a relational database table inside the data warehouse. And as you already know from relational databases, every row generally needs a primary key so that each record can uniquely identified. In data warehousing, the common best practice is to use surrogate keys instead of relying directly on natural keys. Let us make this much more concrete with two example dimension, that is faculty and students. Suppose we have a faculty dimension table. A common naming convention is to add a dimension, that is dim suffix, to dimension tables. It's not mandatory, but honestly it's super useful when you're dealing with large schemas because your dimension tables become very easy to spot immediately. Inside the faculty dimension table, you might have columns like faculty ID and first name and last name and join year, rank, and so on and so forth. Now, the interesting part here is that faculty ID originally came from the source system, and that makes it a natural key. But remember our guideline that in data warehouses, we usually avoid using natural keys as the primary key. Instead, we create an additional column called something called as faculty key that becomes the official primary key. And since it is generated inside the warehouse, it is considered a surrogate key as well. So even though faculty ID still exists in the table, it's no longer serving as the main identifier. The same idea applies to the student dimension. You may still have a student ID and coming from the that is coming from the source system, but the actual primary key in the warehouse would typically be something like a student key, which is a surrogate key generated internally. So make sure that you're comfortable with this difference between the primary keys and foreign keys and natural keys versus surrogate keys, because those concepts are really the foundational of the foundation for the dimensional modeling. Now, when building dimension tables, the general philosophy is that you should include as much useful descriptive information as possible, whether the dimension is faculty, student, department, building, or college. The idea is to make that table a kind of one-stop shop for contextual information. The richer your dimensions are, the easier reportings and analytics become later on. Next, let us talk about something that is really important, that is hierarchical dimensions versus the flat dimension. For example, faculty members belong to departments and departments belong to college. So that is obviously a hierarchy, that is college, department, and then faculty. Students, on the other hand, may not belong to the similar hierarchy, that would considered more of a flat dimension. So this distinction is very important when you are comparing the star schemas and the snowflake schemas. In star schema, hierarchical information is flattened into a single dimension table. So instead of separate tables for faculty, departments, and college, you might store everything together inside one faculty dimension table. That table would contain faculty ID and department ID and college ID and faculty attributes and department attributes and college attributes and so on and so forth. So even though there are multiple natural key inside the table, the official primary key is still the surrogate key and the faculty key. So in a star schema, the hierarchy exists conceptually, but physically the data is denormalized into one table. A snowflake schema, however, works differently. Instead of this, flattening everything, it keeps hierarchy level in its own dimension. That is faculty dimension and then department dimension and the college dimension, for example. Each table has its own primary key, its own descriptive attribute, and now the tables are connected using foreign key. For example, the faculty dimension contains the department key as a foreign key, the department dimension contains the college key as a foreign key, and this kind of creates a chain of relationships between the relationships representing the hierarchy. One thing to notice here is that the highest level in the hierarchy, in this case that is the college, does not need another foreign key because there is no higher level above it, and that is why in snowflake schema lower levels point upward using foreign key, and so structurally the star and snowflake schema differ in two major ways. That is, one is the number of tables, and second the how basically the relationships are represented. A star schema is flatter and simpler. A snowflake schema is much more normalized and hierarchical. Finally, let us look at a slightly more advanced case, that is branching hierarchies. Now imagine a time dimension where days belong to months, but months can belong to both fiscal quarters and fiscal years, or the academic semester or academic years. Now you no longer have a simple straight hierarchy because you have branches. In that situation, a month dimension table may contain multiple foreign key, that is fiscal quarter and a semester key, and that will allow the same month to participate in multiple hierarchical structures at once. So overall, snowflake schema become especially useful when your dimensions contain rich hierarchies or branching relationships, whereas star schemas prioritize simplicity and faster querying by flattening everything together. So as I mentioned earlier, in data warehousing we have different types of fact tables that serve different purposes. Now let us quickly do overview of each one first. Now, but before that, two more basics here. That is, we store the facts, meaning measurements or metrics, inside the fact table, but a fact itself is not the same thing as the fact table, and this distinction is very important as we move forward. So the four main types of fact tables are the transaction fact tables, periodic snapshot fact tables, accumulating snapshot fact tables, and factless fact tables. Now the names sound a bit complex at first, but the ideas are actually pretty straightforward once you see them in action. A transaction fact tables is the one that we are going to cover as a part of this video, and then in the next video we'll cover the other three. So a transaction fact table is probably again is the most easiest to understand. This is where we store the measurements generated from actual transactions happening in the source systems, things like sales and orders and payments and clicks and so on and so forth. Usually this data is stored at a very detailed level inside the warehouse. Then next we have the periodic snapshot fact table. So instead of recording every individual transaction, this table captures the measurements at regular intervals. Think of it like taking a recurring snapshot of the business, maybe daily inventory level or monthly account balances or weekly performance metrics and others. Then comes the third one, that is accumulating snapshot table. This one is somewhat related to periodic snapshots, but the goal here is different. We use it to track the progress of a well defined business process over time as it moves through different stages. For example, an order moving from placed to shipped and then to being delivered. And lastly, we have this factless fact table, which is kind of very interesting name. Even though it is called factless, it's still useful in two major ways. One use case is simply recording that an event or transaction happened, even if there are no actual numeric representation attached to it. The second use case is tracking relationships like coverage and eligibility or participation, basically documenting that a relationship exists even when no measurable event occurred. Now, let us take a look at the first one, that is the transaction fact table that is used in data warehousing, and you will often hear it called as transaction grained fact table as well, where grain simply means the level of detail stored in the table. In most real world data warehouses, transaction fact tables are basically the core of dimensional model. In fact, the majority of fact tables you build will probably fall into this category. At a simple level, a transaction fact table is just a database table where we store the measurable business events, things like sales and payments and orders and clicks and registrations and so on. So these measurements are what we call the facts. Now, a single fact table can contain more than one measurement, but there are specific modeling rules that help decide which facts belong together and which should be separated. And we'll get into those rules later on. But for now, let us take a look at this example here. A tuition payment is clearly something that is measurable. So, in data warehousing terms, it becomes a fact. That means we might create something called as tuition payment fact table. Just like we often suffix the dimension table with something like underscore dim, it is also common to label fact tables clearly as maybe as underscore fact. So they stand out immediately in the model. Now here's the important part. If the table only stores numbers like 7,000 and 6,500 or 7,200 or something like that, those numbers, they are not alone going to tell us much. Every fact needs context. For a tuition payment, the context might include which student made the payment and when the payment happened. Without that information, the measurement is almost meaningless. A beginner might assume that we should store the data exactly like a report, something like, maybe Sally Jackson paid, let us say, $7,000 on August 15, 2020. But that is not how dimensional modeling works. You also would not directly store something like a student ID or raw payment date as your relationships. Instead, in a proper data warehouse design, we use surrogate keys rather than natural keys. Right? So the fact table would actually contain the payment amount, that is the fact, a student surrogate key, a date surrogate key. Those keys then connect the fact table to the related dimension tables. For example, the student key might point to a row in the student dimension table containing Sally Jackson's detail. The date key points to the date key points to a row in the date dimension table for August 15, 2020. Now, that is really the heart of dimensional modeling. The fact table stores the measurement, while the dimension table provides the business context needed to analyze and make decisions from their data. Now, let us continue with our discussion on this transaction fact table with a couple of more reminder. As we saw earlier, a single fact table can store one or multiple facts, but there are some rules that decide which facts actually belong together. You cannot just combine measurements randomly because they may create reporting and analysis problem later on. So the obvious questions are what are those rules? Well, in general, two or more facts can live in the same fact table only if both of these rules are true. That is, the fact are available at the same grain, meaning the same level of detail, and the fact occur simultaneously, meaning they are part of the same business event or process. Now let us make this much more practical with some example. Now let us check the rule number 2 first, that is, do they occur simultaneously? Well, not really, because a bill needs to be generated first and the payment happens later, maybe after a few weeks, or maybe some days, or even just after maybe 5 minutes later, but they are still separate business event, and that difference matters a lot. If we force both of these facts into the same fact table, reporting becomes unnecessarily complicated. We may need SQL workarounds or special joins to avoid duplicated rows or misleading calculations. Why? Because billing and payment are actually two separate business processes, and that leads to a very important principle in dimensional modeling. That is, different business processes should generally have a separate fact tables. So in this scenario, we would create a student billing fact table and the student payment fact table. Both tables can still connect to the same dimension tables like student and date, but the measurements themselves stay separate because the business events are separate as well. Now let us take a look at this example where facts can be stored together. Suppose we have a tuition billing amount and activities fee billed amount. Again, let us apply that rule. Rule 1, same grain. So yes, both the amounts are billed to a specific student on a specific date. Rule 2, simultaneous occurrence. Also yes, because this amount appear together as part of the same billing event, basically the same student bill, since they both belong to the same business process and happen at the same time. Storing them obviously together in a single fact table makes perfect sense in this case. So now one tuition billing fact table can contain, for example, tuition amount and activities fees amount along with foreign keys like student key and date key. But let us finally look at a case where the grain itself is different. Imagine the activities fee also depend on something called as campus that the student attends. Now the student amount is still analyzed by using student and date, but the activities fee is analyzed using the student, the date and campus. That means the two facts are no longer available at the same level of detail, and the moment the grain changes, rule number 1 is violated. So even if both facts are related to billing, they should not be stored together because one fact exists at a higher level of detail than the other one. Now we have already seen how primary keys and foreign key work in dimensional table, but let us apply the same idea to the fact tables as well. Quick recap first, however, a primary key is just a unique identifier for a row in table, doesn't matter whether it's a dimension table or a fact table. A foreign key is basically a reference to the other tables primary key, and that is how the relationships between the tables are created. So for our example, in our student dimension table, we have student underscore key, which acts as both the surrogate key and the primary key. That is the official unique identifier inside the warehouse. But we also have student underscore ID, which is the natural key coming from the original source system, like the student management application where the student record was first created and maintained. So the natural key comes from the real world application, while the warehouse creates its own surrogate key for the internal use. Now here is where the fact tables are little different. In a fact table, the primary key is usually not a single column. Instead, it is a combination of multiple foreign keys that connect the fact table to its related dimension table. Take our tuition billing fact table as an example. It connects to both the student dimension and the date dimension. So the primary key becomes the combination of both the student key, that is student underscore key, and the date underscore key. Why do we need both? Because a single student can receive multiple tuition bills over time, and on a single date, bills can be sent to many different students. So neither key alone is unique, or should I say, neither key alone is enough to uniquely identify a row, but together they are. Now, what is interesting is that these same columns serve two purposes. Together, they form the primary key of the fact table. individually they act as foreign keys pointing back to the related dimension table. So the student underscore key links us to the correct student record, and the date underscore key links us to the exact billing date. And that is why in the diagrams you'll often see both primary key and foreign key marked beside those columns in a fact table, that is PK for primary key and FK for the foreign key in a fact table. At this point, we have covered quite a lot about dimensional modeling and transaction fact tables. We started by understanding the role of dimensions and facts inside our data warehouse, looked at surrogate keys versus natural keys, explored how star schemas and snowflake schemas organize dimensional data differently. We also spent time understanding something that becomes extremely important in real world warehouse design, that is grain. Because once you clearly define the grain of a fact table, a lot of modeling decisions suddenly become much more easier and much more logical. We saw why different business processes like billing and payments usually belong in separate fact tables, and we also looked at how fact tables connect back to the dimension tables using surrogate keys and dimensional relationships. And honestly, these concepts form the foundation for everything else that you'll build later on in data warehousing and analytics engineering. But transaction fact tables are only the one part of the picture that we have covered as a part of this video. In real systems, businesses also run on different things like analyzing trends over time, monitoring long time processes, and sometimes even track the relationships where no numeric measurements exist at all. And that is exactly why the other types of fact tables exist. So in the next video we'll continue this discussion and start exploring the remaining types of fact tables, that is periodic snapshot fact tables, accumulating snapshot fact tables, and factless fact tables. And once you understand how each of them works, you'll start seeing why dimensional modeling is less about memorizing definitions and much more about modeling real business behavior correctly. So whenever you are ready, let us continue with the next video.